Hello there, welcome back. So today we are doing Boolean arithmetic, which is project number 2 of nand2tetris, and the objective of this project would be to take the previously implemented chips, like the elementary chips, the 16-bit variants, and the multi-way variants, all of those, and build these adder chips, which is the half adder, full adder, add 16, and increment 16. Let's get started with the first step, which is the half adder. What is half adder? Well, we take two numbers, binary numbers, and we are supposed to add them and return sum and carry. Let's see how this works. So I'll take the first two values in the first row, add them, and we know 0 plus 0 in the binary gives 0. The sum is 0 and the carry is 0. So I feed it back to the table. Moving ahead with the next row, you get 1 and 0, and this, and so on. So our job is to build a gate such that it takes the inputs A and B and returns sum and carry. How do we implement this black box? What logic gets us the intended result? Let's see. We'll take the sum column first. So you see 0, 1, 1, 0. You should immediately be able to understand or recognize that this value is nothing but XOR logic, A XOR B. So sum is given by A XOR B. Let's look at carry now. Carry, and again you should be able to recognize this. This is nothing but AND logic. So carry is given by A dot B. So we have the sum given by A XOR B and carry given by A dot B. And we have our black box resolved. And the implementation will look something like this. A and B going through XOR, giving out sum. A and B going through AND gate, giving out carry. This was half adder. Now let's move ahead with full adder. What is the logic? So we have three inputs now. You have A, you have B, and you have input carry or carry in. And our job is to generate sum and carry out. You can do this by hand. So you add A, B, and C and generate sum and carry out. Again, looking at the implementation, we are supposed to generate or implement or find out a gate such that it takes A, B, C as input and gives out sum and carry out as output. How can we generate or figure out a logic, figure out a way to do this? Let's look at the sum first. We have a method where we look at the outputs where the sum is 1 and look at the input and try to figure out what is the Boolean logic. So here I'll just take whatever values we have, sum is 1, and look at A, B, C, and if A is 0 we take it as A dash, and if it is 1 we just consider A. So the first set of rows become A dash, B dash, and C in, because A is 0 and B is 0 and C in is 1. Similarly, moving to the next row, it becomes A dash, B, C in dash, and so on. And we're supposed to add all this. So you can pass A is equal to 0, B is equal to 0, and C in is equal to 1, and the sum will come out to be 1. You can test this out. So the entire expression that we have written, we'll try and simplify it further. We'll take A dash common in the first two terms and A common in the last two terms. And the first two terms you can see, you can extrapolate B XOR C in, and in the last two terms become B X NOR, which is exclusive NOR gate. And I'll just put B plus C, B XOR C as P, and you should get A dash P plus AP dash, which is nothing but A XOR P, but P is B XOR Cn, so the sum is nothing but A XOR B XOR C. Similarly, let's try and identify carry. So look at what values of A, B and C give out carry out, and try and generate an expression for that. Let's try and simplify this expression. Cn is common in the first two terms, AB common in the last two terms. Take the common out by the law of commutativity. We know that A plus A dash is 1, so Cn plus C dash becomes 1. So you have Cn A dash B plus AB dash plus AB, and you know A dash B plus AB dash is A XOR B. So you have AB plus Cn times A XOR B. This is the expression for carry, and you have the expression for sum there. And the logic gate or the circuit will look like this. You have two AND gates, one OR gate, and a couple of XOR gates. We'll implement this in HDL in some time. And this was full adder. Moving ahead with the next step, which is the add 16. What is add 16? Let's look at the logic. I'll take a number A, which is of 16 bits, and let me consider a 16-bit example here. I'll take another 16-bit number, call it B. Our job is to generate a logic or create a chip that adds these numbers and returns the total value. How can we do that? The addition in Boolean logic works by taking the least significant bit, which is the rightmost bit, and we start adding and coming towards the most significant bit, which is the leftmost bit. So we'll take the last bit of each number and perform half adder operation. So A is 1, B is 1, so sum is 0 and carry is 1. So we do 0 and take the carry over to the next set of bits. Now you have three values, so we use full adder. So A is 0, B is 0 and carry in is 1. So sum is 1 and carry out as 0. So sum is 1, carry out as 0. The next set of bits, all three values are 0. So full adder A 0, B 0, C in 0. So you have 0 and 0. The next set you have 1, 1, 1, which gives you sum is sum is 1, carry is 1, and so on and so forth. And then continuing this operation, you should be getting this number. We took two 16-bit numbers. In the end, you have one extra bit. So this is called an overflow of the bit, overflow bit. So we ignore this overflow bit in the nand2tetris. So there you have it. Now looking at the implementation, step 1 would be use half adder for the least significant bits and use full adders for rest of the bits and ignore if there is any overflow. Let's look at the next step, which is increment 16. What is increment 16? The logic. A 16 bits, and we have to increment a number just by 1. How can we do that? By using the existing chips already. So we convert increment into a 16-bit number such as this. The least significant bit value is 1, the rest of them is 0. And we can do add 16, where A is the 16-bit value and B is also the 16-bit value, which is increment. So you should be getting this value. And then in the implementation, consider 60 increment as a 16-bit input, and then use add 16, pass A and pass increment. So this was the logical implementation or the theoretical implementation of the adder chips. Now let's look at the HDL implementation. Let's get started with the HDL implementation. Project number 2, and we'll do the half adder. What is half adder? We got sum, which is the XOR logic, and carry is AND logic. So you pass A and B, out as sum, A and B, output is carry. Run this. There you have it, simulation successful. Let's look at full adder. Yeah. So full adder requires two XOR chips, one AND chip and one OR chip. So sum is A XOR B XOR C in. So I'll do A XOR B. I'll just call that XOR A B. Okay. This doesn't take underscores. I'll just call XOR AB. Pass this again and C and sum. There you have it. That's your sum value A XOR B XOR C, and you need A XOR B into C in. So do this A XOR B and C in. That I'll just call it temporary. So or you need this. AB plus Cn times A XOR B. Looks like we need another AND. So we need A, B, I'll just call AND AB. Okay, so you need AND AB plus temp to give you out carry. We run this. Yeah, there you have it. Simulation successful. Let's look at add 16. Add 16, yeah. Half adder for least significant bits, which is half adder. The indexing starts from the rightmost, so you have A0, B0, carry is C1, and sum is output of 0. Yeah. And full adder for the rest of the bits. Full adder. So there's 16 bits, and one of the bits is already handled. So let me go ahead and 3, 4, 5. Yeah, there you have it, 15 bits. Let me just go ahead and do this. Replace all A's with A is equal to A of, and B is equal to of. C is C. Sum is output of, and carry is C. Got a general template here. Now let's start filling the values. So full adder takes 1 and 1 and takes carry 1. Sum output is 1 and carry is 2. So 2, 2, 2, 2 and 3. Let me just go ahead and fill in all the values now. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So all of the carry bits are utilized except for the last bit, which is ignored. So each carry is used in the next full added chip. Yeah, and C16 is given out. Let's run this. Hopefully there won't be any bugs. Yeah, there you have it. Simulation successful. Let's go with the increment 16. As we've already seen, we just have to perform add 16 where A is input. The B, the least significant bit, is true or 1, and B 1 through 15 is set to false, and output is fed back to output pin. Simple. We are utilizing add 16 by setting the rightmost value to 1 and rest of them to be false. Let's run this. Yeah, simulation successful. There you have it. The HDL implementation of project 2A, which is the adder chips, is complete. In the next video, we'll look at how we can build an arithmetic logic unit using the previously implemented chips. Yeah, there you go. Thank you.